What's up, peoples? This video is intended to help you with static equilibrium. Now, we've done this in the past, and in the past it was sum of the forces in the x and y are zero, but now we are studying rotation, which means the sum of the torques must be zero. I have two examples in this video. This first one's going to be super easy, and then there's one that's a little bit more realistic, something you can expect on an assessment or a better homework problem, and then we'll sum up some of the key points at the end of the video. So the first thing we're going to do is we have this object here, and we are going to draw a free body diagram of the object. And I know in the past we've drawn free body diagrams of like their dots, but this is a beam. So we're going to draw a free body diagram of all the forces acting on the beam. You've got the support force here on the left, an applied force A, and then you have another one holding it up, FB. You've got 10 kilograms pushing down on the on the beam. So it's a force of gravity caused by the 10, which if you just do quick math, mg, 10 times 9.8 is 98 newtons. I kind of like to put that in my free body diagram. I trust that you can do calculations like that, and I don't need to see the work. And you have the force of gravity created by the 5, which will be 49 newtons. And it says here that we have a uniform beam with mass 10 kilograms. Uniform means that the beam has a constant density throughout. So if we were going to draw the force of gravity acting on the beam, actually right now I'm going to change this to 20. My bad, that's supposed to be 20. And back to the point, which is if I draw the force of gravity acting on the beam, if it's uniform, we can say that that acts in the middle of the beam here. So this would be the force of gravity on the beam at 20 kilograms is 196 newtons. Terrific. Now, step 2 is to choose a pivot point or a reference point. It's a point about which you are going to pretend that this object could be rotating. And you'll want to choose a location where you have at least one unknown. And right now our unknowns are FA and FB. Choosing a reference point on the end here seems more appealing to me because I could take all my distances with respect to this end here. So this will be 1 meter. This will be 4 meters. This would be, what do we got going on here? 5 meters. And the whole distance away is 8 meters. All right, let's do a little shenanigans here. When you're doing these equilibrium problems, your goal is to sum the forces in the x and the y. They should add up to 0, and sum the torques. They should add up to 0 as well. Now, this is stupid, but I'm writing it. If I sum the forces in the x equals 0 newtons, well, there are no forces in the x, so I really don't have to do anything here. Let's sum some forces in the y, shall we? And they should add up to 0. Looking at my free body diagram, I've got the applied force up, I've got FB up, I've got 98 newtons down, 196 down, 49 newtons down, and that adds up to 0 newtons. This is part of the reason why I chose to do, calculate the gravity and just put it in diagram. I don't need to see 10 times 9.8 unless you feel it necessary. So right now, best I could do is apply the force of A plus the force of B. It's going to end up equaling 343 newtons. All right, kind of stuck there. Now I want to do the sum of the torques about the pivot point. And you'll remember, torque is force times distance times the sine of the angle. Each of these forces is applied at 90 degrees. Sine of 90 equals 1. So if you want to write sine 90, go ahead. I will not be doing it. So I'm going to sum the torques, and they should add up to 0 newton meters. Okay, you don't need to do this, but the FA is acting at a distance of 0 meters, so it's not applying any torque. And as we discussed in class, clockwise is considered negative and counterclockwise is considered positive. All 3 gravitational forces are going to try to make this beam rotate about the pivot point that way, which is clockwise. So they would be considered negative torques. The FB is trying to make it rotate counterclockwise around that point, so it would be considered positive. So I'm going to do the applied force B acting at a distance of 5 meters. The other torques are going to be negative. Not that it really matters because the other side of the equation is 0, and you can just move them over and make them positive, or just say like FB is equal to the other torques, what I've got going on here, but I'll write it out properly. Minus 98 newtons acting at a distance of 1 meter, excuse me, minus 196 newtons acting at a distance of 4 meters. Sorry, I didn't do spacing very well here. Minus 49 newtons acting at a distance of 8 meters. And this should add up to 0 Newton meters, as in that is the total value of the torque. Now, if you look at what we've got here, the only thing you don't know in this entire expression is FB. So the FB ends up being 255 newtons, which you can then throw in here, and you would find out that FA is equal to, I believe, 88 newtons. That's a pretty easy example. We had a horizontal beam, no X-forces, and X-force. Sorry, every time I say X-force, I think of Deadpool. Sorry, that took a long time. Deadpool 2, X-force. All right, I'm done. I wasted so much of your time just now. Anyway, there's no X-forces. There are Y-forces. And we did the sum of the torques, but none of them are at angles. So let's move down to a better example. And before I do, I'm going to hit save on this so I don't lose anything. As I scroll down here, I've got a better example. We've got clearly what is a traffic light based on my unbelievable artistic abilities. And we are going to draw a free body diagram of the diagonal beam in which all the forces are acting on that beam. So here we go. There's my beam. I should draw it more like 60 degrees. Sorry, that's still not great. Try that again. Straightish line. All right, let's draw the forces acting on this beam. In class, we usually start with, because most people pick this up, you got the force of gravity caused by the light, which would be 196 newtons. Again, I'm doing 20 times 9.8. We assume this is a uniform beam, so its center of mass it would be right in the middle, and 50 times 9.8 is 490. The tension is applied here to the left. Now, to truly be in equilibrium, the sum of the forces in the X have to be 0, and right now they're not. And when you see locations like this, where I'm filling in here, right there, that's what I'm talking about, that's like a hinge. Any problems with hinges or welding right there, you can assume that that area applies both a horizontal and vertical force. I think that's the case almost every time. So to make the sum of the forces 0 in the X, there needs to be some X force to the right here, acting at that green dot I drew. And you can tell also in the Y forces, we have 2 forces down, but nothing up, so there needs to be an Fy here as well. I'm going to fill in some angles. This is 60 degrees, which makes this 60 degrees. This is 30 degrees. This is 30 degrees. Alrighty, are you ready for some fun? Now that you've done that, you have to choose a reference point. Personally, my reference point, you want to choose a location where you have unknowns. Right now, we don't know Fx, Fy, or Ft. I'm choosing down here because it's going to eliminate 2 of my unknowns. Let's do forces in the X. Here we go. If I sum the forces in the X, I've got Fx minus Ft equals 0. So not much I can do there. If I sum the forces in the Y, come on, give me a color to work with. We'll go with green. Sum the forces in the Y equals 0 newtons. We've got Fy minus 490 newtons minus 196 newtons equals 0 newtons. Check it out. I know what Fy is. It's 686 newtons. And then we must do the sum of the torques. Okay, sum of the torques. About a reference point. Sum of the torques equals 0 Newton meters. Now, do you need to write Fx times 0 meters plus Fy times 0 meters? Not for me, you don't. But I'm just writing it because I'm a professional, and I'm saying that neither of those cause any torque. You can tell from the picture that both gravitational forces will make it rotate clockwise around our pivot point. Those would be considered negative torques. Ft makes this try to go around counterclockwise, so that would be positive. All right, here we go. So we've got Ft, 60 degrees, 1 meter. Now, do you need to write Fx times 0 meters plus Fy times 0 meters? Not for me, you don't. But I'm just writing it because I'm a professional, and I'm saying that neither of those cause any torque. You can tell from the picture that both gravitational forces will make it rotate clockwise around our pivot point. Those would be considered negative torques. Ft makes this try to go around counterclockwise, so that would be positive. acting at a distance L, that's what it says in the picture originally, sine theta. Torque is FR sine theta. Well, the angle is 60 degrees. Minus, 196, acting at a distance L. The angle between the force and the beam or the object of interest is 30 degrees. So that's going to be sine 30. Minus 490, acting at a distance L over 2. That's where the center of mass is. Sine 30 equals 0 Newton meters. I'm running off the page for whatever reason. I decided to write really big. The L will divide out. There's an L in every term. L, L, L. If you're wondering if there's no L in 0, that's okay. Remember, we're dividing everything by L. 0 times L is still 0. Or if it makes you feel better, move these to the other side. Now they're positive. Every term has an L. Anyway, once you get that, guess what? You can get that the tension force is equal to, this is a very big coincidence, 255 newtons. 255 was an answer from a previous problem. Once you get that, you can throw it right in here, and you know that Fx is also 255 newtons. So that's about it, peoples. Let's go review this really quickly. All right. When you're doing these problems, you want to draw an FBD of the object. It's usually a beam at the moment. For these rotational equilibrium problems, you can expect a beam of some kind. Problems in the future will give like height to width ratios of say like 4:3. All right, just realize that that means cosine is 3/5, sine is 4/5. Your goal mathematically is to do the sum of the forces in the x and the y add up to 0, but also the sum of the torques is 0. You must choose a reference point, and it should eliminate one or more unknowns. I usually choose an end if I can. And then, of course, you can do a little algebra, and you're going to have a good time. Like, have a lot of fun with that. It says enjoy, so you should enjoy. A question that comes up often is, I know there's a problem in the homework in the future where there's a beam, and then there's a force, like a tension force, and it acts at 25 degrees to the horizontal. But it's acting at 90 degrees to the beam. And people are asking, you know, what angle do I use for what? Nothing's changed. When you do your sum of the forces in the x, you're just going to write negative ft cosine 25 because it's the angle with respect to the horizontal, the x-axis. When you do your sum of the forces in the y, you can do what you always did, which is going to be ft sine 25, and you're done. When it comes to the torque, torque is ft sine theta, but it's the angle between the applied force and the beam or the object, which I've just said is 90 degrees. So when you're doing the sum of the torques for this, you would say ft times L, which I believe, or R, which I believe in this problem is 3/4 L. You'll know the homework problem when you see it. Sine 90, which is 1. Just wanted to bring that to your attention. Other than that, I'm sorry this video was so long. I hope it was helpful in some way, shape, or form. Personally, I would give this about 3 out of 5 stars, and I wouldn't change a thing.